Better? Ah, good. Okay, I just read the slide. Good. So, discontinue rules. I just moved to NBME, so I'm still very happy to say that I made the right choice. I moved there in January. I have more time for research. I was heavily involved in international assessments, and that brought me to new fields. And one of them was something that is discontinue rules. Those discontinue rules are in some way somewhat maybe on this, not quite in the center of what you would call a computer adaptive test, even though they have some features of adaptivity and they could be viewed as something that is actually an early form of that. And they're used quite a bit in paper-based and in some computer-based assessments. So I'll talk a little bit about that. I will show some results on ignorability. I will talk about what happens when you use the current scoring rules, what kind of biases you might see. I will talk about violations of local independence, and then I will just propose a very simple fix of what's going currently on in many ability tests, and do a little summary at the end. So here we go. Discontinue rules in ability testing. First of all, of course, I had to somehow legitimize myself. What does it have to do with ICAT? I hope somewhere there's a mouse here. There's maybe this one. Well, first of all, you also have omitted items in CATs. So there might be something of interest for people who have to struggle with missing or omitted responses here. Discontinue rules also use skipped items as wrong responses, essentially, and assume it's more or less reasonable to do that. Finally, discontinue rules are something that you could call an early form of adaptive testing used in IQ testing in an actually wide range of products. And maybe in the end, we can convince some of those test publishers to actually move to a real CAT or to use something like a shadow test approach rather than doing what they are doing right now. I already mentioned, so they're used in paper and computer-based tests. Basically, it's a very simple rule. You present the items in an increasing order of difficulty. You discontinue after some wrong responses. It's pre-specified in the test manual, obviously. And then you just assign incorrect responses after that. And we pretend then that these responses are actually observed. We just treat them as wrong. There's no partially correct, no nothing. It's a very simple rule. And if you look at this stuff, so it's actually used in quite a bit, and this is just a few examples here. Stanford Binet, Kaufman Assessment Battery for Children, Adults and Adolescents. This is a test that I learned when I was studying in Germany, Hamburg Wechsler Intelligenz Test for Kinder, children. So a lot of these versions actually use this kind of rules. The nonverbal intelligence test revision still uses it. And here's a book that talks about brief intelligence tests. Some of them use only 2 wrong responses, and then they assign all wrong responses after that. So 2 wrong responses in a row and you're out, which is a really tough rule, obviously. So why do we use this rule? So we have so many testing programs using this thing because it might seem plausible. Yeah, everything after that is wrong. Yeah, why not? The problem is there's actually research on that, and one paper does a simulation study, finds that if you do this, you actually use what seems plausible, and you get a big bias in ability estimates, and you get differences in item difficulty estimates. But the paper still says, yeah, but these items can't really be ignorable because they are there. They must be wrong. So they really seem to already think what we have now is correct. So we just need to find justification for that. They use a simulation, and in the end, the simulation more or less contradicts what they think is true, and they still continue with the fact that we should still continue using this rule. Why is that? Maybe because it's a little bit complex. So I'll try to explain it here a little bit more in terms of a tree of what's happening. So you have a number of previous responses, and you have two paths. If they are all wrong, you assign the next response with probability 1 to be wrong. If some of them are not wrong, with probability 1 minus the probability of all wrong, you go to the next item and observe it. And you observe the next item with probability of 0 given the true score, or theta or whatever, or probability of 1. You observe a correct response. So here you have a deterministic path, which is never good in probabilistic models, and it's also never good if you really believe that humans can actually act on even hard items and guess and maybe just get it and maybe just work a little harder than in those previous 2 to 5 items. Formally, it's also not that bad, but it's still in some ways a very simple rule. So in the first few items, you simply get no missing data at all. This describes the missing data process. If the previous missing indicator was 0, so there was no missing data, you check whether the previous items were missing, all of them, all L of them. If the previous item was already missing, this next missing data indicator also gets a 1. So that means you get a string of zeros, which say, well, there is no missing data, all is observed, and then you get a string of 1s following that. Everything is missing after that. So what we do then is we are rescoring essentially the complete data that we don't see, that becomes something like latent responses, into the observed data. So we observe up to a certain point, and then we continue with missing once the missing indicator turns from 0 to 1. Yeah, and obviously we only have equality if this missing data rule never applies, so the discontinue rule never gets triggered. So why do I tell you this? Because what happens with that is bad. When you look at the Rubin's definition of missing data as missing completely at random, missing at random, and missing not at random, you see that missing completely at random is if essentially the missing data indicator are independent of the observed responses. Missing at random looks familiar if you look at this previous slide here. The missing data indicators depend only on the observed subset of responses, or where we actually have those previous responses all observed. Missing not at random is if the missing data indicators depend on those latent responses as well, also where we don't observe the data. So in very simple words, there's good indication that this missing data is actually ignorable because we see those previous responses and we decide whether we go on or not, only based on the previous responses, not on anything latent, not even on a theta estimate or anything. The same happens if we look at this formal definition and this kind of blueprint of a proof of whether something is ignorable or not. Essentially, there are two conditions. The parameter space of the complete data model and the missing data model are distinct and can be separately estimated, or there are even no parameters for the missing data model because everything is based on the observed. And the distribution of the missing data process given the complete data equals the distribution of the missing data given only the observed data. And that's exactly what we have. So we have ignorability. However, all those intelligence tests do as if the data are not ignorable and treat those responses as wrong. So there's a little bit of a contradiction there, which leads to trouble. Yeah, that's pretty much what I just said. One additional thing, this missingness is monotone, so from no missing to missing, there's just one jumping point. And essentially you can group people into different groups where this missing data starts. So in conclusion, we have ignorability. Discontinued items can be ignored and shouldn't be treated as wrong. And we see bad things coming out of that. So next thing is the effects on this current scoring rule. What happens actually then? So the bias in the expected score is pretty easy to show. Under this condition, using this discontinue rule, the expected score of each item after the initial L items is lower than the expected score of the complete data, or of the X variables. So we have, for example, we can do this for any item without any model. We just do a little bit of a decomposition in raw score groups, partial scores up to the jth item. And we look at the probability of the j plus first item. And for the discontinue rule, we get essentially this probability of a correct response, which says, well, this is a correct response only if the latent response was correct, or if somebody would have continued with a correct response, somebody of that whatever ability or raw score group, and the missing data indicator based on the previous L responses is 0. So we still observe this thing in the form of actually this gets mapped to the Y. This is an AND condition. This means that this thing is smaller unless you go only in the first few items, which I will show next. So if you can't really apply the discontinue rule, you will have equality. In all other cases, once the discontinue rule can be applied, this is really truly smaller than this probability. So you have a smaller expected value on every item. That obviously also implies that all those partial sums on the additional items after a certain score is reached also have a smaller expected value than under the full data. So what do we do with that? What we can do in terms of, if we wanted to use IRT, we can also do the same game with classical test theory. We could use a multiple group model and essentially account for those difficulty differences. So we are treating them as wrong. We essentially use wrongly the assumption that we actually know what's happening, even though it's ignorable. All students were not affected by this discontinue rule at the same spot, so they actually end up with different types of item difficulties or item parameters in IRT. And what happens, you can already see it, if we then actually compare this in terms of IRT parameters. The yellow one is the discontinue rule, so the difficulty just goes up and up and up and diverges from the estimates we get under complete data, the estimates under treating them as missing data, and the estimates under a specific multiple group model where we assume partial item invariance. So where we just say, well, up until here you have the same item parameters as the others. Once your discontinue rule holds, the slope is 0, and the item parameter is whatever. It's just plus something really big. And then we just take the common item parameters from the partial invariance model. So we get great agreement in all these three models. Only when we apply the discontinue rule, we get a problem, because we essentially make the items harder than they should be. Yeah, the same can be done with CTT. I have a paper where I can actually show you the amount of bias. It's an recursive formula. You can calculate that actually. The easy way to treat it is just use missing data instead of wrong. And then there's one final consequence. There's actually also violation of local independence. And I'm just showing this graphically. I hope I'm not running out of time. So when you just look at response residual correlations and you do whatever kind of simulation, I had 50 items at a unidimensional model. I think it was a 2PL or a Rush model, doesn't really matter. The response residuals are very close to 0. So there's, once you account for the latent trait, nothing is left. Conditional independence, as we all like it and know it and always want it. Under simulation conditions, we always get that. Once we apply the discontinue rule, this happens. It's not huge. I could probably have triggered a little bit more if I wanted. I used 5 items. If I only used 2 items for the discontinue rule, I would probably have had higher residual correlations. So what you see is all these not really light blue dots here show that there are residual correlations, and they're quite systematic. So altogether what we get is we have bias in ability estimates and in item difficulty estimates. We have violations of local independency. We essentially have items on the later items depend on earlier items or sums of earlier items, which are essentially used to see whether the testing stops. And if we would treat them as missing, we would still preserve quasi-independence, but we don't. So the last thing, proposed rule, why does it need fixing? It needs fixing because some of the brief intelligence tests use just 2 responses. And that really gets a lot of people in trouble because it's easy to get 2 responses wrong. Other respondents might get more lucky. And you get also essentially different populations with different item parameters that are working towards their scoring. The very simple fix is really just that we can say, well, imputation, as always, is one good approach, or if you use IRT, just ignore it. If you really need those scores, use the last observed score, use those groups, equivalency groups in some scores. If you use CTT, for IRT, use some estimator, WLE, MLE, if you have enough items. And if needed, calculate just the expected score on those items, or even use multiple imputations. And then you would get something that is still consistent with expectations, even if you would see the full data, and it's consistent across the different groups where the discontinue rule applies. So in summary, missing data is ignorable, and again, there are papers out there, and maybe that's my little speech against only doing simulation studies. Simulation studies cannot show proof. You can actually prove that the data is ignorable. In the simulation study, you will only see it's the least biased, and you can still discuss it away because somehow there's a plausibility argument that treating them as wrong is still better than not treating them at all. I don't know which argument that might be. Treating them as missing as wrong violates local independency, gives item bias, gives ability estimation bias, and yeah, we can just impute or use CAT. Okay, that's it. Thanks.
Without electricity monitoring, just estimate based on you observe the numbers and items.
Exactly. I think imputations are only you need complete data. It's really just those models can handle missing at random, so there's no need to impute anything. Perfectly fine under any data variable model that handles this stuff. But many people like complete data. In that case, it's the case.
Yeah. I just wonder whether you bring this to an MSP context, and whether you apply those discontinuity rules within the basis of an MSP, whether there is still ignorability. I'll have to talk about that.
I didn't think about it because it was really just.
Here you assume that you have a random sample from a population.
Yeah, here it's a simple case, it's a simple design. I think I have to think about this a little bit more. I would assume that it's never a good idea to treat something that you didn't observe and you know what it could be. So in that case, I would still probably go for ignoring the missing data because this it's also kind of very somewhat artificial question. Would you even apply something that is continued to shorten the stage in multi-stage test? I don't know why I wanted to do that. something very similar. You just use a subset of items in any tab, and you ignore what's before and what's after. If you would just order the items that you gave to somebody in the tab, you also see that the easy items, the ones that are too easy, tend to be skipped. There's also the precondition rule, which I didn't talk about. I think the Vexler is also using that. In developmental testing, if you're old enough, I don't give you the first 5 items. I just assume they're all correct, which is also a small thing. I don't think there's much foundation to these assumptions because another time, all these tests all move to computers, so there's really no reason to engage that rule anymore because you can either put adaptive things or you put the statements that are short enough and still give enough information to do it right.
It's not quite clear that you have a very specific case of discontinuation of time. But generally, I don't do the assumption of non-ignorability. It depends on the reason why it is. For instance, if it's a technical failure of the system, completely independent of how they assume that way, it's clear that it's talking about. If it candidate certainly becomes ill, what if the candidate expects that the main portion of the test is going to be bad? It doesn't depend on the actual missing scores, it depends on the subjectively expected missing scores. And I've checked the literature, I haven't found any opinion there.
In those cases, when you assume that they expect the items to be too hard for them, and if that expectation is actually grounded in at least some probability.
The expectation itself may be wrong.
Yeah, in that case, it's then we still at
I don't know what to do there.
Yeah, but I think you can see it a little bit in those missing propensity models, where you would actually then apply another data dimension to try to model whether the missingness or the skipping is either independent of the ability or whether that actually has a correlation or whether there are some other systematic. I think there's pretty strong indication that self-imposed missingness tends to be less benign. This is a very benign case. I think if people have the choice to skip or not, it's much less benign because they either do it because subject to cost are too heavy, which is an open-ended item I think to skip, or because I think I might not be able to solve it in time, and that can be ability related, and then there's nothing better for it, because it's less benign, still use the model.
The modeling is the main difficult. Difficult, that's the only thing.